What came before the Big Bang? Can we rewind the universe to its first breath? This film traces our origins from a hot, dense beginning to everything we see today. You'll see the evidence, space expanding, and the universe's baby picture, the cosmic microwave background. We'll learn how the first elements formed and why galaxies drift apart as space stretches. Then the frontier. Did before even exist when time itself began? Bounces, brains, maybe a multiverse. Bold ideas awaiting tests. Now, expansion. Welcome to the grandest story ever told. We will use simple words and clear ideas to guide you through this cosmic epic, a narrative that stretches across billions of years and unfathomable distances. This isn't just a story about distant stars and galaxies, it's a story about us. It is a story about where everything came from, including you. Every atom in your body, the iron in your blood, the calcium in your bones, was forged in the heart of a star that lived and died long before our sun was born. We are, in the most literal sense, children of the cosmos. The quest to understand our origins is a fundamental part of being human. For millennia, our ancestors gazed at the same celestial lights, weaving myths and legends to explain the universe and our place within it. That same innate curiosity drives us today. We look up at the night sky, a vast and sparkling tapestry, a window into the deep past. The light from the nearest stars has traveled for years to reach our eyes. The light from distant galaxies has journeyed for millions, even billions of years. And as we stare into that profound depth, we cannot help but ask the ultimate question: where did all of this come from? The Big Bang Theory is our best scientific answer to that question. It's important to clarify what the Big Bang is and what it isn't. It's not an explosion in space, but rather an expansion of space itself, from an incredibly hot, dense state. It provides a powerful and elegant framework that explains the universe we observe today. This theory successfully predicted the existence of the cosmic microwave background radiation, the faint afterglow of the initial hot state, and the observed abundances of the lightest elements, like hydrogen and helium. It accounts for the universe's large-scale structure, from the grand dance of galactic superclusters arranged in a vast cosmic web, to the humble atoms that make up our own bodies, our planet, and our star. It connects the largest scales of the cosmos with the smallest particles of matter in a single, coherent story of cosmic evolution. This single theory weaves together observations from astronomy, cosmology, and particle physics into one unified narrative. But this journey of understanding is not just about looking backward into the distant past. It is also about understanding the very nature of science itself. Science is a human endeavor, driven by curiosity, creativity, and a relentless pursuit of evidence. Science is not a collection of unchanging facts written in a book. It is a dynamic and self-correcting process. It is a process of discovery, of building models to explain the world, and then rigorously testing those models against the evidence that nature provides. When a theory, like the Big Bang, survives decades of intense scrutiny and makes successful predictions, our confidence in it grows. Yet, when we get to the question of before the Big Bang, we reach the absolute frontier of our knowledge. Here our established laws of physics break down, and we enter a realm of pure theory and mathematical exploration. Here we find bold ideas, like the concept of a multiverse, where our universe is just one bubble in a vast cosmic foam of other universes. We find speculative theories, such as string theory or cyclic models, which propose that our Big Bang was the result of a collision between higher dimensional brains or part of an endless cycle of expansion and contraction. These ideas are tantalizing, but for now, they remain beyond our ability to test. And so, we have the honest admission that we do not yet have all the answers, and that is okay. In fact, it is the engine of science. The existence of these profound mysteries is what inspires the next generation of thinkers, astronomers, and physicists to keep asking questions, to keep looking up, and to continue this incredible human journey of discovery. Let's get one thing straight from the start. The Big Bang was not a big explosion. The name is a bit of a misnomer, a catchy phrase that stuck. An explosion happens at a specific location in space and expands outward into that space. But the Big Bang was different. It was the beginning of space itself. It was an event that happened everywhere at once because the entire universe, all of space, was contained within that initial, infinitesimally small point. It was the rapid, ongoing expansion of space itself. carrying matter and energy along for the ride. Imagine a loaf of raisin bread dough rising in an oven. The raisins are like galaxies. As the dough expands, every raisin moves away from every other raisin. A raisin on one side of the loaf sees all the other raisins moving away from it, but there is no center to the expansion within the dough. The expansion is happening everywhere. In the same way, from our vantage point in the Milky Way galaxy, we see other galaxies moving away from us. This is not because we are at the center of the universe, it is because the fabric of space itself is stretching, everywhere. This idea of an expanding universe has profound consequences. If the universe is getting bigger today, it means that yesterday it was smaller, and the day before that, it was smaller still. If you run the cosmic movie in reverse, all the galaxies come rushing back together. You rewind past the birth of stars, past the formation of atoms, all the way back. As you go further back, the universe gets not only smaller but also hotter and denser. All the matter and energy we see today, spread across billions of light years, was once squeezed into an unimaginably hot and dense state. This is the core concept of the Big Bang. It is not a tale of how something came from nothing. It is a description of how our universe evolved from a state of extreme heat and density into the vast, cool, and structured cosmos we inhabit today. The theory tells us about the how and the when of this transformation. It is a story of expansion and cooling. Let us dial the clock back to the very beginning, to the first fractions of a second after the expansion began. At this moment, the universe was a searingly hot, dense plasma, a chaotic soup of fundamental particles and pure energy. The temperature was trillions upon trillions of degrees, far hotter than the core of our sun. In this extreme environment, matter and energy were interchangeable, converting back and forth, according to Einstein's famous equation, E equals mc squared. The familiar particles we know today, protons, neutrons, could not yet hold together. It was a time of pure, unbridled cosmic energy. As space expanded, it cooled. This cooling was the most important thing happening in the early universe. Within the first microsecond, the universe had cooled enough for the fundamental particles, quarks gluons, to bind together and form the first protons and neutrons. These are the building blocks of atomic nuclei. For the next few minutes, the entire universe was like a giant nuclear fusion reactor. Section 4. The universe's baby picture. Evidence we can see. How can we be so confident about events that happened 13.8 billion years ago? It's a question that cuts to the very heart of cosmology. We cannot build a time machine to witness the universe's birth. Instead, we must act as cosmic detectives, searching for ancient clues left behind by the cosmos itself. And fortunately for us, we have evidence. Powerful, compelling evidence. A fossil relic from a time when the entire universe was a fundamentally different place. The most spectacular piece of proof is the afterglow of that moment when the fog cleared. The light that was released 380,000 years after the Big Bang is still all around us. This isn't a metaphor, it is a physical reality. Photons from that primordial era have been traveling across the cosmos, unimpeded, for billions of years. Today, they fall upon the Earth from every direction, a constant, gentle rain of ancient light. As the universe has expanded over billions of years, that light has stretched. Its wavelength has gotten longer, shifting it from the brilliant visible light of a searingly hot plasma into the cool, invisible microwave part of the electromagnetic spectrum. This phenomenon, known as cosmological redshift, is a direct consequence of the expansion of space itself. We call it the cosmic microwave background, or the CMB. When astronomers Arno Penzias and Robert Wilson first detected the CMB in the 1960s, they found a faint, uniform microwave hiss coming from every direction in the sky. They were using a large, horn antenna at Bell Labs, and initially, they thought the noise was an equipment malfunction, or perhaps even interference from nearby pigeons. But after meticulously ruling out every possible terrestrial source, they realized they had stumbled upon something profound. It was the echo of creation, the oldest light in the universe. This discovery provided the first direct observational evidence for the Big Bang theory and earned them the Nobel Prize in Physics. It is, effectively, the universe's baby picture. A snapshot of the cosmos when it was just an infant, long before the first stars or galaxies had formed. Since that initial discovery, our telescopes like the COBE, WMAP, and Planck satellites have mapped this radiation in exquisite detail. These instruments are designed to be incredibly sensitive, capable of detecting temperature differences of just a few millionths of a degree. These maps show tiny temperature fluctuations in the CMB. The average temperature of this background radiation is a frigid 2.725 Kelvin, just a few degrees above absolute zero, but it is not perfectly uniform. There are minuscule variations, represented by the different colors in these images, that represent the seeds of all cosmic structure. These are the imprints of quantum fluctuations from the very first moments of the universe, expanded to astronomical scales. The slightly denser and therefore slightly cooler regions in this early picture were the places where gravity would later pull matter together to form the first stars, galaxies, and the vast cosmic web of galaxy clusters we see today. The slightly less dense, hotter regions would become the great cosmic voids. In this single image, we see the blueprint for the entire future evolution of the cosmos. While the cosmic microwave background provides a snapshot of the infant universe, another powerful line of evidence for the Big Bang comes from observing the cosmos as it is today. This evidence was uncovered through the groundbreaking work of American astronomer Edwin Hubble in the 1920s. Working at the cutting edge of astronomical technology at the Mount Wilson Observatory in California, Hubble used the most powerful telescopes of his era to gaze deeper into space than anyone had before. At the time, most scientists believed our Milky Way galaxy constituted the entire universe. But Hubble's observations of faint, fuzzy patches of light, then called spiral nebulae, proved they were in fact distant galaxies, each a sprawling island of stars just like our own. But he didn't stop there. He began to meticulously measure the light coming from these galaxies. By analyzing their light spectra, he could determine whether they were moving toward or away from us, and how fast. What he discovered was astonishing. With very few exceptions, he observed that distant galaxies all appear to be moving away from us. It wasn't a random scattering, it was a clear, organized pattern. More than that, he found a direct relationship. The farther away a galaxy is, the faster it is receding from us. A galaxy twice as far away is moving twice as fast. One 3 times as far is moving 3 times as fast. This precise mathematical relationship, now known as Hubble's law, is exactly what you would expect to see in a universe that is expanding everywhere. It's helpful to imagine raisins in a loaf of baking bread. As the dough expands, every raisin moves away from every other raisin. From the perspective of any single raisin, all the others appear to be receding, and the ones farthest away move the fastest. This isn't because the raisins are moving the dough, but because the dough itself, the very fabric of space, is expanding. The mechanism for this measurement is a phenomenon called redshift. As a galaxy moves away from us, the light waves it emits are stretched during their long journey across the cosmos. By measuring the light from these galaxies, we see it is stretched to longer, redder wavelengths. This cosmic redshift is the telltale sign of an expanding universe, the primary observation that led to the Big Bang model in the first place. It was the first concrete evidence that our universe had a dynamic history, that it wasn't static and eternal, but had a beginning. Finally, the theory makes another set of incredibly specific, testable predictions. These relate not to the vastness of space, but to the very first moments of time, and the creation of matter itself. This pillar of evidence is known as Big Bang nucleosynthesis. The theory allows us to calculate the physical conditions, the temperature and density, of the universe when it was just a few minutes old. In this primordial furnace, the universe was a seething soup of fundamental particles. As it cooled, protons and neutrons began to fuse together to form the first atomic nuclei. The calculations based on these conditions in the first few minutes of the Big Bang predict that this process should have produced a very specific chemical composition for the early universe, about 75% hydrogen, the simplest element, and 25% helium, with only trace amounts of other light elements like lithium and deuterium. This prediction is incredibly bold. It suggests that the fundamental makeup of all the matter we see today was determined in the first few minutes of existence. But how could we possibly test it? The universe has been evolving for billions of years, with stars constantly forging heavier elements and changing the cosmic chemistry. The key is to find places that are as untouched by this stellar processing as possible. So, when astronomers look at the oldest stars and most pristine gas clouds in the universe, places that have not been significantly altered by later stellar processes, they are essentially looking at fossilized remnants of the early cosmos. By analyzing the light from these ancient objects, they can measure their chemical composition with incredible precision, and what they find is a stunning confirmation of the theory. Across the sky, in every direction we look, these ancient objects show abundances that match the Big Bang's predictions with remarkable accuracy. The 75 to 25% split between hydrogen and helium is observed exactly as calculated. This beautiful agreement between theory and observation, across multiple, independent lines of evidence, gives us great confidence that the Big Bang model is on the right track, providing a powerful and coherent story of our cosmic origins. The great unknown. What came before? We have a robust, evidence-backed story for our universe starting about 13.8 billion years ago. The narrative holds together from the first microseconds onward, but when we try to push back further, to the moment of the Big Bang itself, the singularity, our current laws of physics break down. A singularity is not a physical object, it's a point in our math where equations blow up. Infinities. It is a sign our theory is incomplete. General relativity works for stars and galaxies, but it fails at the extreme early universe conditions. That breakdown means the question, what came before the Big Bang, can't be answered by our current proven physics. It lies outside what we can directly test or observe. As an analogy, asking what came before might be like asking what's north of the North Pole. If time began with the Big Bang, before may have no meaning. Time is a property of our universe. Without the universe, before and after may not apply. That's one simple possibility. This is where science moves from solid ground to the shifting sands of speculation. To go further, we need a new theory. Something that unites Einstein's gravity with quantum mechanics. That hypothetical framework is called quantum gravity. Scientists are exploring candidates. String theory loop, quantum gravity, but none are complete or experimentally verified. These ideas are our best tools to peek behind the curtain of the Big Bang. Section 6. Bounces, Bubbles, Beginnings, Exploring the Before. One of the most intriguing ideas from quantum gravity research is the concept of a quantum fluctuation. In the strange world of quantum mechanics, empty space is not truly empty. It is a roiling sea of potential, where particles and energy can pop into and out of existence for fleeting moments. Some physicists have proposed that our entire universe may have originated as one such fluctuation. A tiny bubble of spacetime could have spontaneously emerged from a pre-existing quantum vacuum, and then, through a process called cosmic inflation, rapidly expanded to an enormous size, triggering what we call the Big Bang. Another compelling idea is the cyclical or bouncing universe. In this scenario, our Big Bang was not the beginning of everything, but simply one event in an eternal cycle of expansion and contraction. As it collapsed, quantum effects could have become dominant, preventing it from crushing down into a true singularity. Instead, it would have bounced, rebounding outward to begin a new cycle of expansion, our universe. A third family of ideas comes from string theory, which posits that the fundamental constituents of reality are not point-like particles but tiny, vibrating strings of energy. In some versions of this theory, our universe is a three-dimensional brain, short for membrane, existing within a higher dimensional space. The Big Bang could have been triggered by the collision of our brain with another brain. This ekpyrotic model, named after the Greek word for a conflagration, envisions the beginning of our cosmos not as a singular point, but as a dramatic, universe-spanning event in a larger, hidden reality. These are just a few of the ideas being explored. Others include a multiverse concept, where our universe is just one of countless bubbles, each with potentially different laws of physics, constantly being born. What these speculative models have in common is that they try to replace the singularity of the Big Bang with a physical process that can be described by a more fundamental theory. They are all attempts to answer the question of before in a scientifically coherent way. For now, they remain beautiful mathematical constructs, awaiting a future test that could confirm or falsify them. Section 7, The Journey Continues, Embracing the Cosmic Mystery. So, what existed before the Big Bang? The honest answer is, we do not know for sure. We have a powerful evidence-based story, the Big Bang model. It describes the evolution of our universe from its first moments to the present day. We can see its echoes in the cosmic microwave background. We can see its echoes in the retreat of distant galaxies. This story is a monumental achievement of human intellect and curiosity. It tells us that everything we see and know emerged from a hot, dense state. That state began expanding 13.8 billion years ago. This is a fact, grounded in observation. But the question of before pushes us beyond the edge of our observational map. It takes us to a place where our current laws of physics are no longer sufficient guides.